Hello everyone. So in today's video, I am going to go over this paper titled ToxiGen, a large-scale machine-generated dataset for adversarial and implicit hate speech detection by Thomas Hartwigson, Sadia Gabriel, Hamid Palani, Martin Sapp, Dipankar Ray, and East Kamar. I'm really sorry if I mispronounced any of those names. And you can see they are all from top tier research institutes and organizations. So MIT, University of Washington, Microsoft Research, Allen Institute for AI, Carnegie Mellon, and Microsoft. So Microsoft Research and Microsoft. Again, a disclaimer: this paper discusses and contains content that can be offensive or upsetting. So if you don't really want to see that stuff, I'll recommend you don't continue ahead. So without further wait, let's just get right into it. And you can see this paper is fairly recent, 10 May 2022. So this is barely a month old when it was released. So the abstract. Toxic language detection systems often falsely flag text that contains minority group mentions as toxic, as those groups are often the targets of online hate. So if you research this stuff, you'll probably know that machines often learn false correlations between the mention of a group and it being toxic. For instance, I can just say minority XYZ is pretty good, they are very hospitable, but the machine might just detect the mention of the minority and think, okay, he must be saying something bad. Such over-reliance on spurious correlations also causes systems to struggle with detecting implicitly toxic language. To help mitigate these issues, we create ToxiGen, a new large-scale and machine-generated dataset of 274,000 toxic and benign statements about 13 minority groups. So I guess this part is pretty self-explanatory. We develop a demonstration-based prompting framework and an adversarial classifier in the loop decoding method to generate subtly toxic and benign text with massive pre-trained language model. Controlling machine generation in the way allows controlling machine generation in this way allows Toxygen to cover implicitly toxic text at a larger scale and about more demographic groups than previous sources of human written text. So when you ask humans to create such examples, then there's a limit, right? You cannot have humans generate text in say hundreds and thousands of sentences with only a limited amount of people. That is very resource driven. We conduct a human evaluation on a challenging subset of Toxygen and find that annotators struggle to distinguish machine generated text from human written text, which is good in itself because then you can use that for simulating real world sentences. Using three publicly available datasets, we show that fine-tuning a toxicity classifier on our data improves its performance on human-written data substantially. So this is also pretty good because what they're doing is they're using the publicly available datasets and fine-tuning the toxicity classifier on the data that they've created using synthetic methods. They also demonstrate that ToxiGen can be used to fight machine-generated toxicity as fine-tuning improves the classifier significantly on our evaluation subset. So overall, this seems like a pretty huge paper, and given that it's giving so many new data points to train on, and this might just open a whole new world of like ideas to use this new data set on. Alright, so the introduction. Toxic language detectors often over rely on minority identity mentions while flagging a statement as toxic without considering the deeper semantic meaning of the statement. This is what I just discussed. Also, in this work, they use minority to refer to social and demographic groups that are frequently the targets of oppression, discrimination, or prejudice from a US socio-cultural perspective. So I guess that is just because they're based in the United States and there's much more literature for the United States. This can lead to severe underdetection of subtle hate. Example, uh, so you've got this example. They have been bred to be good at sports and entertainment, but not much else. So this is, you can see this is subtle hate because this is hateful. I can't explain why, but I hope you get why this is hateful. And over detection of benign statements. So if someone says child abuse is wrong, racism is wrong, sexism is wrong, then there's nothing wrong with this statement. He's just pointing out the truth, but machine translation, generated machine classifiers might just flag this as toxic. Importantly, such biases in toxicity detection risk further marginalization or censoring minority groups. So then, because if a minority group is being mentioned and it's being continuously flagged as toxic, then you're automatically censoring tweets related to them even when they are not toxic. So they introduced ToxiGen, a large-scale machine-generated dataset of 274,186 toxic and benign statements. To create this dataset, we leveraged a massive retrained model GPT-3, which is known to produce close to human-like text, but also easily generates socially biased and toxic content. So, if you've seen some previous literature, you might know that due to the very nature of the training data, so GPT-3 was trained on huge amounts of data scoured from the internet. It meant that it learns biases also present on the internet. That is why it often generated toxic text. While such human-like bias and toxicity poses real threats, we use this undesirable behavior in models like GPT-3 to improve existing toxic language classifiers, providing a path forward for mitigating systemic bias. Created using demonstration-based prompting and pre-trained toxicity classifiers, ToxiGen covers about 135,000 toxic and 135,000 benign statements, about 13 minority identity groups such as African American, women, LGBTQ plus folks, etc. So you can see the dataset is balanced and they're leveraging the downside of large scale language models to enhance their dataset and create their dataset essentially. Using this machine generated approach has two advantages over scraping posts from the web as done by previous work. So all these are the pioneering works of hate speech, such as Davidson et al., Fonta et al. All of these showcased for the very first time how you can run classifiers to detect hate speech. First, it allows us to limit spurious identity toxicity correlations by generating equal number of toxic benign statements for each demographic group. So this is basically this is a pretty interesting point as well. So suppose you have 30, let's just take their case only, they have 13 minority groups. Suppose you have 100,000 tweets for one minority group and only 1,000 tweets for the other. So when you train a model, then the model is going to learn this skewed data, and it will then generate these spurious identity toxicity correlations. So it will think that if identity X is mentioned, then it is much more likely to be toxic than identity Y when it is not really the case. So when you generate sentences, you can control how many you want for each minority group, including those that are often overlooked in toxic language corpora. So Native Americans. This is quite true. In hindsight, I think I've never seen any paper refer to Native Americans and toxicity surrounding them. Second, machine generation and careful prompting enables us to generate implicit toxicity, so without swear words or slurs. This is also pretty important because for explicit toxicity, you already have tons of data sets. A major one being the hate explain dataset. So these are the ones which are hard to detect, and thus they are often missing in toxic language corpora. Indeed, 98.2% of ToxiGen statements are implicit, that is devoid of explicit profanity, slurs, or swear words. So this will make our models more robust to the real world because the adversaries or the people who are propagating hate speech have learned that using explicit mentions can get their accounts banned, but using subtle hatefulness can get the message across without getting their accounts banned. Alright. To generate a challenging subset of toxygen, we introduce Alice, an adversarial classifier in the loop detection decoding algorithm. Alright. So we use Alice to control the toxicity of output text by pitting a toxicity classifier against a text generator during beam search decoding. Given a toxic prompt, we can encourage generation to be less toxic based on the classifier scores. Similarly, we can share a language model with neutral prompting towards higher toxicity generations. Our experiments with 5 publicly available toxicity classifiers show that they generated sentences in both cases above full toxicity classifiers. So we'll get it more into detail when we reach the section on Alice. But essentially, Alice is used to control the toxicity of output text and that is done by pitting the toxicity classifier against a text generated during the beam search decoding, which is essentially how you decode the output sentences. And with that, you can steer the direction of your output to any level of hatefulness that you want. So if you have a look at these statements and their hate scores, so suppose you take this sentence, there is a big difference between a Muslim and a terrorist. This is a benign sentence, but it's regarded as being toxic 73% with a probability of 73% by perspective API. Similarly, you have say this sentence, they have been bred to be good at sports and entertainment, but not much else. So this is a toxic sentence, but it's only given a 13% toxicity rate. All right. So we validate the quality of our machine generated dataset through a comprehensive human evaluation. Our results show that on a sample of 792 machine generated sentences, 90% could be mistaken for human written text, which is pretty good. We also find that generated data indeed contains a wide variety of specific references to the minority group mentioned in the prompts. So that is also pretty good because you want your sentences to be more robust or have more different kinds of references. This indicates that the data generation approaches with or without alias successfully control the generation towards the desired toxicity and minority group mention. Further, experimental results demonstrate that fine-tuning existing classifiers and ToxiGen consistently improve performance from 7 to 19% on three existing human-written implicit toxic datasets: implicit hate corpus, social bias frames, and Dynahate. So this is also a pretty huge leap. This indicates that the dataset generated in this work and the approaches for generating data provide major steps towards improving toxicity classifiers and could potentially be used downstream to address the issues from biased machine generation or neutral toxic degeneration. We release our code and ToxiGen dataset publicly. We also include two models pre-trained on ToxiGen along with our human evaluations. So the code is available and the GitHub repo is also linked here. The full form for Alice is here: adversarial language imitation with constraint exemplars. And they've also given a disclaimer, so you can see this Delphi. This does not give a probability. So at this point of time, it was not available. But the Delphi author had confirmed that this will also be available soon. Alright. So implicit hate against minority groups. Detecting implicit toxicity about minority groups like stereotyping, microaggressions remain an elusive goal for NLP systems. One key challenge is that, in contrast to explicit toxicity, implicit toxicity is not marked by the use of profanity or swear words, is sometimes positive in sentiment, and is generally harder to detect or collect at scale. Nonetheless, implicitly toxic language about minority or marginalized groups is often psychologically damaging to members of those groups. This is, of course, pretty understandable, I guess. So I'm not going to go into this once again because I've already discussed this in some capacity in the abstract section. It can also reinforce stereotypical or hateful perceptions of them, right? A second challenge for detecting subtle toxicity about minority groups is that minority mentions are more often the target of social biases and toxicity. As such, minority mentions often co-occur with toxicity labels in datasets scraped from online platforms. For example, over 93% mentions of Jewish folk in SAP et al. Are toxic. In turn, models are trained on such data can exploit the spurious minority toxicity correlation instead of considering the deeper semantics of text. Importantly, the spurious correlations are also learned by large language models, which are known to produce stereotypical, biased, or toxic content when prompted with minority mentions. Given that the main mitigation approach to prevent LLM from generating toxic language is to train new classifiers to detect such language, these classifiers also learn the spurious correlations and start blocking most language referencing minority groups. This risks erasure. So you can see that this problem propagates downwards. To fix this problem, you create another problem. With ToxiGen, we aim for generating a large-scale dataset that represent implicit toxicity while balancing between toxic and benign statements to address the gaps of previous work. As shown in Table 1, existing datasets contain large amount of explicit toxicity, while valuable, most previous work has relied on scraping data from online platforms, which leads to dataset imbalances with respect to minority mentioning posts that are toxic versus benign. Examples are collected at scale using keyword-based scraping, so you will look for some certain slurs or swear words, bootstrap scraping approaches, and machine versus human adversarial data collection, among others. In contrast, using large language models to generate a dataset allows us to control the minority group mentioned, as well as implicitness at larger scale. So if you look at, say, this dataset from Brightfeller et al. 2019, you can see uh, you have 99% implicit, but it's 100% hateful. If you take a look at tweet BLM from which is 9,000 tweets, 99% implicit, only 33% hateful. So if you look at these data sets, you can see that there is no balance between implicit hateful and implicit benign. So while the ToxiGen dataset is 98.2% implicit and perfectly balanced between hateful and benign statements. All right. So creating ToxiGen. To create ToxiGen, we use demonstration-based prompting for large language models, encouraging a text generator to produce both toxic and benign statements that mention minority groups without using explicit language. We introduce a classifier in the loop decoding method based on constrained beam search, Alice, which along with samples generated without Alice contributes to generating a challenging subset of ToxiGen. Using these methods, we generate a massive set of statements, over 274,000, containing equal number of toxic and benign sentences for 13 minority groups. Alright, so table 2. So this is table 2. These are the statistics. So if you have a look, say for the Asian community, you have 10,000 benign, roughly 10,000 toxic, and same for almost all of them. So they are in a similar range, though not exactly the same, but you can't really expect them to have exactly the same, right? If you need them to be exactly the same, you can just truncate them. Right. So prompt engineering. Toxicgen is generated by prompting a language model to produce both benign and toxic statements that include mentions of minority group by name and contain mainly implicit language which does not include profanity or slurs. So this is pretty much implicit speech generation. To achieve this, we perform demonstration-based prompt engineering. So what you do is you acquire example sentences, you pass them to the LLM, and then collect their response. For example, when showing 10 sentences mentioning Muslim folks neutrally, GPT often responds with similar neutral sentences. So you can see that they're just leveraging the quick nature of these LLMs to adjust themselves to the input prompts. That is essentially demonstration based prompt engineering, because you're prompting the LLM based on some demonstrating examples. So demonstration-based prompting. Prompts are text fragments passed into language models that can encourage certain behaviors. However, designing prompts is notoriously challenging. While there are several approaches for prompting pre-training LLMs, a recent and promising direction is demonstration-based prompting. Here, example statements are passed to an LLM, encouraging it to produce a similar but distinct statement. For example, to encourage LLMs to produce benign statements about Asian people, we might use the following example. Many impactful people are of Asian descent. There are hundreds of Asian cultures. And to engineer prompts that lead to high quality group mentioning toxic and benign statements at scale, we first gather and curate set of examples. So first they'll need to create such examples that then are passed to the LLM to create statements. So to generate both benign and toxic responses from LLMs that mention minority groups, we first collect many examples, intuitively given many examples of benign sentences that mention one particular group. A language model can be used to produce more. For benign prompts, we encourage realistic text generation and include diverse voices by collecting benign sentences from blog posts and news articles that mention a group. However, finding large amount of such data at scale is challenging. That is why implicit datasets are hard to acquire. So just going back, if you have a look at these datasets, you can see how much smaller they are. So you might think that, oh, this is 80,000, but only 26% of that is implicit. Right, so where were we? Yeah, So to build a large enough set of demonstrations, we begin with a small number of examples from the wild, then engage a human in the loop process, collect some demonstrations, pass them to the language model, comb through many responses, and add the best examples to a growing set. So you have like some seed sentences and then they generate more sentences for prompts. Ensuring that a set of examples consistently produces benign responses that still mention the targeted minority group is challenging, and so we iterate this loop many times, sampling random subsets of our example to serve as prompts and observing the responses. So this way we collect 20 to 50 demonstration sentences per group, all of which we release. So initially they have these 20 to 50 sentences which they then use to prompt. To encourage implicit toxicity from a LLM, we find examples of human written sentences with implicit toxicity towards each group from hate forums and Reddit. So then they repeat the human in the loop process to expand our set of examples. So similar to this data rate. Overall, by repeating this process for both toxic and benign examples for all 13 target groups, we create 26 set of prompts with two benign and toxic per target group. So I guess this was pretty understandable. We had a look at this table already. So now let's jump into Alice. So Alice attacking toxicity classifiers with adversarial decoding. So demonstration based prompting alone consistently produces toxic and benign statements about minority groups. There is no guarantee that these statements will be challenging to existing toxicity detectors. So this is the important part where Alice comes in. Therefore, we develop Alice, a variant of constrained beam search during decoding that generates sentences that are adversarial to a given pre-trained toxicity classifier. What does this mean? This basically means that they give it a pre-trained toxicity classifier, and Alice basically tries to promote a sample generation which are able to fool this toxicity classifier. So Alice creates an adversarial game between a pre-trained language model and a toxicity classifier, so PLM and CLF, during constrained beam search decoding. So in many CBS settings, constraints are added during beam search decoding to force the model to either include or exclude a specific word or group of words in the output. With Alice, we instead want to enforce soft constraints on the probability coming from a given toxicity classifier during beam search. So basically what they're saying is the log likelihood of a word being generated given some previous words is the log likelihood. So this is the probability of uh, the classifier and the probability of the language model. Both it's proportionate to both of them multiplied by some factors which are hyperparameters. So lambda L and lambda C denote hyperparameters that determine the respective contribution of the language model and classify to the decoding scoring function. By using this weighted combination, we can steer generation towards a higher or lower probability of toxicity without sacrificing coherence of the language model. So to create examples that challenge existing toxicity classifier, they have two setups. So they want false negatives. So we use toxic prompts to encourage the language model to generate toxic outputs, then maximize the classifier's probability of the benign class during beam search. So what this basically means is the model is generating toxic sentences, but the classifier is predicting them to be benign or more likely to predict them to be benign. So that is why they're false negatives because they're actually toxic but not being marked as toxic. For false positives, they steer the model to generate benign sentences, but they maximize the probability of the toxic class during beam search. So in the first approach, we are also able to detoxify model outputs when the classifier successfully steers the generation towards non-toxic languages. Let me just read this. In the first approach, we are also able to detoxify model outputs when the classifier successfully steers the generation towards non-toxic language. Because since this is non-toxic language, then this means that the model outputs are detoxified. And Alice is showcased in figure 2. So you have a sentence uh, and let's just go step by step. You create sentence, you sample the top k from the language model, then you create partial sequences, then you try to minimize the hit probability, and you also adversarially try to use the classifier model So you have a generation and a candidate token. You pass it through Alice. Sorry, you pass it through the classifier model, which generates a score. You utilize that score with the language model's prompts to get a weighted combination, and you pass that here as well. So that is the modified uh, selection rate, I guess, or the modified weight for each candidate token during the beam search decoding process. Alright, so the decoding details. We train ToxiGen data with and without Alice. Without Alice, they simply use a top K decoding alone with our toxic and benign prompts. With Alice, they use HateBird fine-tuned offensive val model from Caselli et al. 2021 as a toxicity classifier. So this is a pretty recent work. This model covers a range of direct and veiled offense types. They use GPT-3 for the language model. For decoding, they set both the hyperparameters to zero point 0.5, a maximum generation length of 30 tokens, beam size of 10, and temperature of zero point 0.9. Temperature is basically for a softmax. Due to limitations imposed by the OpenAI GPT-3 API on accessing log probabilities for the full vocabulary model, we restrict the vocabulary size to the top 100 tokens and then resample from the allowed tokens. So the tokens not appearing in the prompt using top K. Because OpenAI does not allow them to get the log probabilities on the entire model vocabulary. So now let's look at the ToxiGen statistics. Statistics are presented in table 2. In our final dataset, generation length varies significantly, and as expected, almost all the statements are implicit. As we show in appendix 4 or section 4, the Alice generated data is successful at attacking the given toxicity classifier, contributing a challenging adversarial subset of ToxiGen. In the release data, we split off the test set that is validated by human annotators. Alright, so human validation of ToxiGen. To ensure the quality of ToxiGen, we conduct human validation experiments and create ToxiGen human eval, a human validated test set. Specifically, we investigate the reliability of our prompt-based and Alice-based methods at generating human-like statements and controlling statements, toxicity, and minority group mentioned. Additionally, we measure the effectiveness of Alice generated versus the top K generated at fooling classifiers. So for the human validation design for each generated statement, we ask the annotators various questions described below and take into account multiple dimensions of how toxic machine generated language presents a potential harm to readers. So Appendix B has the full details for this. So the perceived hatefulness with respect to human annotators or AI authored text. We first ask annotators to guess whether the system's authors was a human or an AI system, so that is human or AI. Then we ask whether the statement would be harmful to anyone if a AI wrote it or if a human wrote it. That they write that as harmful if AI and harmful if human. Then they hypothesize that readers may have different standards for machine generated text from human written text because, of course, people may have a lower standard for machines or even a higher, who knows. For all question measuring harmfulness of text, we consider potential harm on a 1 to 5 scale, 1 being clearly benign and 5 indicating very offensive. Then you have perceived intent of the writer. We ask readers whether statements are likely intended to be harmful, since some biased statements can be positively intended. So you have benevolent sexism. Additionally, we ask if the statement exhibit a positive stereotype, which is also harmful because you don't want the model to learn stereotypes. Or even if the stereotype is good, you don't want stereotypes in itself to propagate. Then you have detailed harm explanation. To better understand how harm may be perpetrated against a minority group, we ask readers in-depth questions about text content, and we ask whether or not the statement is lewd or sexual, whether and how it references a targeted group or other group, which whether it claims to be factual or opinion. So all of these are also parameters which they've asked the human annotators. Uh, right. So constructing ToxiGen human eval, they selected 792 statements such that no training statement had cosine similarity above zero point 0.7 with any test statement. Each test statement was generated by 3 annotators from a pool of 156 pre-qualified annotators from Amazon Mechanical Turk. Then if you look at the human annotator inter-annotator agreement, it was higher than or equal to previous works on hate speech annotation. So Flice's kappa of 0.46, and Krippendorf's alpha of 0.64. In 55.17% of cases, all three annotators agree, while a majority agree in 93.4, which is pretty good. Now the human validation results. Firstly, we find that our machine-generated statements are largely indistinguishable from human-written statements. For example, see Table 3, human annotators often predict that a text is generated by a human. In fact, on average, 90.5% of machine-generated examples are thought to be human-written by a majority of annotators. We also note that harmful text confuse readers slightly more than non-harmful text. 92.9% of toxic examples are mislabeled as human compared to 90.2 for non-toxic. Most toxic examples are also hate speech. While opinions are common in both toxic and non-toxic, most fact-claiming text is non-toxic. So you can have a look at the average score and human or AI. So if it was a human or if it was a AI and so on. And you also get the intent. So for these examples. Second, we find that demonstration-based prompting reliably generates toxic and benign statements about minority groups. Further, for the machine-generated examples, we find that 30.2% are harmful, while only 4% are ambiguous. This indicates that data are sufficiently toxic or benign. We also find that all identity groups covered by the dataset were represented in the human study, and observed that the identity group referenced by the prompt is generally the same as the group referenced by the corresponding ToxiGen text. Though there is some deviation, this is likely due to GPT-3 conflating identities or mentioning multiple groups. Interestingly, there is no significant difference in toxicity when we account for whether annotators perceive scores as written by human or AI. So they give it a same score where the irrespective of whether a human wrote it or AI wrote it. This finding indicates that a machine generated text is perceived as similar harmful to human text. We also find that most common framing tactic is moral judgment or questioning the morality of an identity group, which has been linked to toxicity by prior work as well. So if we compare the generation method, as further validation, we investigate whether Alice generated statements are more adversarial compared to top K generated. So for 125 randomly selected prompts, 62 toxic and 63 non-toxic, we generate two statements, one with Alice and one without. So that would be the top K sampling one. We then collect annotations for 250 statements using the setup described in above and get the toxicity scores from HateBot. We find that top K sample sentences for top K sample sentences, the prompt label indeed matches the desired label. So 95.2% of non-toxic samples and 67 toxic. For Alice, 40.3% of toxic samples match the prompt label and 92% of non-toxic examples match. We also find that Alice succeeds in fooling HateBot. So 26.4% of Alice decoded sentences fooled HateBot versus 16.8 of top K, which indeed makes it more challenging. Finally, Alice is effective for detoxifying generated text. So the average human annotated toxicity score for Alice decoded sentences with a toxic prompt is 2.97 compared to 3.75 for top K, which is a significant difference. This is statistically significant. Alice therefore leads to harder, more ambiguous examples. We greatly expand on these findings in Appendix C with a large-scale human evaluation, approximately 10,000 samples comparing sentences generated with and without Alice. On improving toxicity classifiers to further show the usefulness of ToxiGen, they fine-tune the widely used HateBot and Tox Detect Roberta models on training portion of ToxiGen using the prompt labels as proxies for true toxicity label. Then we compare the performance of the out-of-the-box model to these fine-tuned on ToxiGen on three publicly available human-written datasets, so implicit hate corpus, social bias frames, and Dyna hate, as well as the evaluation portion of our machine-generated dataset. To evaluate the toxic contribution of each decoding method, we also split ToxiGen into equal number of Alice-generated and top-K-generated samples. So the results are in table 4. We show that fine-tuning both of these improves performance across all datasets. The improvement on human-written datasets shows that ToxiGen can be used to improve existing classifiers, helping them better tackle the challenging human-generated implicit toxicity detection task. Fine-tuned hate robot performs strongly on ToxiGen human eval, demonstrating that our data can successfully help guard against machine-generated toxicity. So you can see Alice plus top case dominating almost everywhere except in one case where it's equivalent to only Alice. Now the conclusions. In this work, we used a large language model to create and release ToxiGen, a large-scale balanced and implicit toxic language dataset. ToxiGen is far larger than previous datasets, containing over 274,000 sentences, and is more diverse, including mention of 13 minority groups at scale. The generated samples are balanced in terms of number of benign and toxic samples for each group. We propose Alice an adversarial decoding scheme to evaluate robustness of toxicity classifiers and generate sentences to attack them, and showed the effectiveness of Alice on a number of publicly available toxicity detection systems. In our experiments, we showed that fine-tuning pre-trained hate classifiers and ToxiGen can improve performance on three popular human-generated toxicity datasets. We also conducted a human study on the subset of ToxiGen, verifying that our generation methods successfully create challenging statements that an annotator struggles to distinguish from human written text. So 90.5% of machine generated examples were thought to be human written. So this is pretty neat. This dataset, I believe, is going to be used extensively now in literature and elsewhere, and they've shown pretty good scores. They've shown pretty good balance in the dataset, and overall, the work was a pretty interesting work to go through. Of course, now they have the societal and ethical considerations which you have with such datasets. So they've mentioned that there is a potential for misuse, but their ultimate aim is to shift power dynamics to target of oppression. Therefore, we do not consider identity dimensions that are historically the agent of oppression. Also, please note that there is still a lot that is this dataset is not capturing about toxic language. Our annotations might not capture the full complexity, and more work needs to be done. Uh, Now, Alice, the proposed method in this work attacks content filters via an adversarial game. It is important to leverage this and similar approach to improve content filters and prevent large-scale attacks against sensitive platforms. Improving toxicity detection. So, effective classifiers for machine biases are required to combat the scale of online harm. Without such systems, minority groups are likely to be targeted. The current work is a significant step in that direction. So, moving from binary detection tasks to focus on more nuanced labeling systems will be more crucial in developing responsible systems and relationship to policy. The topic of detecting and mitigating toxicity is relevant to the ongoing work uh, in the space of policy and legislation for AI. Carefully crafted policy and regulation can play an important role in providing oversight into the development of such technologies. Getting this right carries a crucial importance for the society as errors in content moderation can disproportionately affect minority groups as they propagate. We saw in an example before. We see a path forward in these tools and techniques, which those presented in this work are paired with human expertise and well-labeled policy and regulation, bringing scalable and reliable solution to practice. Therefore, they encourage the role of an LP community to play in this interdisciplinary effort. You also have the responsible AI consideration. So there's a lot that this dataset is not capturing. The annotations might not cover all nuances. Problematic language is also fundamentally a human-centered problem and should be studied in conjunction with human experience. There is need for multidisciplinary work to better understand these aspects. Also note that this dataset only captures implicit toxicity, which is hate speech, and due to its large-scale nature can naturally be noisy. Our goal in this project is to provide the community with means to improve toxicity detection on implicit toxic language for the identified minority group, and there exists limitation to this dataset and models trained on it, which can potentially be the subject of future research, for example, including more target groups, a combination of them, and so on. Also, acknowledgements they thank the Azure AI platform and Misha Bilenko for sponsoring this work, Microsoft Research for supporting the human study, and Alexandra Oltino for her feedback on human evaluation. And they also thank all the crowd workers. I won't be going into the appendix, so there's a lot of stuff in the appendix as well. I'll read that in my free time, but I guess I'll recommend you read because a lot of stuff that they mentioned in the paper, they've also said that it's described in more detail in the supplementary material. So thank you guys for joining in. Hope to see you again next time as well.